Now that we have the uniqueness of perpendiculars, I want to give some results of this. The first, if alpha is equal to infinity, so we actually do not have a bounded distance, distance can be as big as we want it to be, then there is a unique perpendicular to a given line and passing through a given external point. We don't have that weird case where there are infinitely many perpendiculars, so perpendiculars will always be unique in that case. The second result, if the distance between P and Q is equal to alpha over 2 for some point Q on my line L, and I know that the line PQ is perpendicular to L at Q, then for every point X on L, Px is equal to alpha over 2, and the line Px is perpendicular to L. The idea, here I have my sphere, I have my point P at the top and my point Q on the equator. So I know the distance between P and Q is equal to alpha over 2, and I know that this line is perpendicular. Then if I pick any other point on this line X, and I try to draw the line between P and X, it will still be perpendicular, and the distance between P and X will still be equal to alpha over 2. My next result has something to do with triangles. If we know the legs of an isosceles triangle each have length alpha over 2, then the base angles are both right angles, and conversely. Here is a generic example where I have my triangle with 3 sides. I know the length of these 2 sides right here are each alpha over 2. Then, by my previous result, each of these are right angles. They're both perpendicular, which would tell me both my base angles are right angles. And it goes the other way as well. If I know that these 2 angles are right angles, it guarantees that both of those sides are of length alpha over 2. My next one, if a right triangle has legs of length alpha over 2, then it is a trirectangular triangle, meaning all 3 right angles. So here I have my first leg of the triangle, which is length alpha over 2, which means it has a right angle. I'm then going to travel over to a length that's alpha over 2 from that point and draw the next side down so that now all 3 of my angles are right angles. And this is only possible on the sphere. I now want to define something known as the foot. I'm going to let L be a line and A be any point not on that line. I'm then going to let F be the point on my line such that the line between A and F is perpendicular to L. In this case, my Euclidean case, I would just draw the unique perpendicular passing through A. Not a great picture, but that's okay. And the point where this perpendicular passes through the line is F. And we have the same idea in the spherical case. If I take a line and any point not on the line, I want to draw the perpendicular, and where that perpendicular intersects my line is F. And it's important to note that if A actually occurs at the pole, then this point F is not unique. There's going to be a lot of them since all of the lines will be perpendicular. Then this point F is known as the foot of A on our line L. This now allows us to talk about distance between a line and a point. The distance between a line L and a point A is AF, the distance between A and its foot. And in fact, the distance from the point A to any point on the line has the smallest value for the foot. So the actual distance from a point A to a line is the minimum possible distance between A and any point on that line, which is guaranteed to actually be this point here, F, the foot. So the foot allows us to actually be able to talk about distance from a point to a line.